So welcome back to the course on multi-agent learning. We discussed Bayesian play, the fourth part. Which culminates in the results of Kalai and Lehrer and Dubins and Blackwell on the true distribution of play, concept of true distribution of play as it actually happens, and subjective distribution of play as participants see it. So the reply rules together induce a true distribution of play, mu, on the path of play as follows. If G is the actual reply profile, so the reply rules as all participants maintain them, then we, for the sake of efficiency, we can establish it by the Bayesian, by sorting out all multiple histories here and making it one history here. And then a reply rule, a reply profile, so that all the reply rules of all participants induce a probability distribution mu on the set of all histories inductively in a straightforward manner. The probability of history H with last action X is simply the probability of the history itself times the probability of playing action X or action profile X based on this history. So that's what happens here. Let me hark back. That's what happens here. Here. No. Here. Here. That's exactly what happens here. So these are the probability of the individual actions given the history, and these are the probabilities of the successive histories. So that's exactly what happens here. Now, we now have established a probability measure on the set of all histories. You see, all histories receive a probability induced by the reply profile. Now, this probability measure on the set of all histories, from this probability measure we can construct a probability measure on the set of all paths of plays. First, we establish a correspondence between the set of all possible histories and the set of all possible plays. If you define a certain history, given a certain history, you can define the set of continuations of H. The set of continuations of H, you can define it as all possible paths of play. If you restrict that path of play to the length of the history, you will get back that history. So this is very straightforward and the only possible definition, I would say, of set of continuation of possible histories. And of course, the set of all continuations yield the set of all play paths. So the set of continuations indeed cover the set of all play paths. Now conversely, if you have a play path, then you define the restriction of that play path to a certain round is of course a history. Now the probability measure mu on H induces an almost measure mu prime on the continuations of H through, well, the straightforward definition. Define the continuation, well, the probability or the measure of the continuation of that particular history. Define that as the measure, the true measure of the history itself. So all continuations of a history receive the same probability as the history itself. They have to share that probability. Okay. Now, there is a result in probability theory called the Carathéodory's extension theorem that says that such a pre-measure can be extended to a proper probability measure that is a sigma algebra on that set. So this pseudo measure or pre-measure can be extended to a true probability measure, and then we have a probability measure on all paths of play. Now, the beliefs on the reply rules of other players, together with I's own reply rule, forms also some sort of reply profile. So these are the beliefs of the second player combined with its, not its belief, but its actual reply rule of the second player. And that represents the further course of play as the second player sees it. Now we have just seen that the vector of all the reply rules, G, generates a true distribution of play, mu, on omega, on a set of all possible play paths. Similarly, player's I conception of play here, of course, generate a subjective, so in the same manner as here, a subjective distribution of play. And let us call that for player 2 mu sub 2. So for player 2 this is a subjective distribution of play, and for player 1 it's like so. So we have on the one hand the true distribution of play, and on the other hand for each player a subjective distribution of play, mu I. Now, given a play path, omega, we would like to say something like, if the number of rounds proceeds in due course, then every player's subjective view on play at a certain round approximate in some sense the true distribution of play, like so. So dot means for any set, for any event. So the true distribution, the subjective views of play approximate the true distribution of play in the long run. So in order to formulate this result, we have to introduce the notion of domination of probability measures. You have two probability measures, mu and tau. Then tau is set to dominate mu if, whenever mu has a positive probability, then tau has as well. So whenever mu is positive, tau is as well. And if both measures dominate one another, then we say they're equivalent. Now, if the subjective view of play of every player dominates the true distribution of play, so if every player assigns positive probabilities to every realization deemed possible by the true distribution of play, then the player I's beliefs are said to contain a grain of truth on actual play. So if mu dominates nu, then we can prove that mu is expressive as nu. So all probabilities expressed in nu can be expressed in terms of mu. What did I just said? All probabilities, so if nu is dominated by mu, then nu can be expressed in terms of mu by some intermediate function which has nice properties. Measurable, I don't know whether that should be measurable in terms of mu or nu. I suppose that should be in terms of, well, I don't know. But at least if I beliefs contain a grain of truth on actual play, then mu's subjective view of play is as expressive as the true distribution of play. So every player keeps accounts, or every player deems it possible, deems every play path represented by mu possible. And that is meant by grain of truth. So I's beliefs are very expressive. They deem it possible that every possible play path expressed by mu has a positive probability. Now, to work towards first result, the theorem of Blackwell and Dubins, we have true distribution of play. We have another distribution of play. Then this other distribution of play is said to merge with the true distribution of play if, for almost all play paths omega, it is the case that in the long run the conditionalized probabilities on those continuations of the restricted play paths, so actually those histories, the distance between those two probabilities converge to zero. We would like to denote histories here, but that's not possible because the two probability distributions work on play paths. So through some kind of trick, we should convert play paths into histories, and then we can talk about histories here, and then we translate them back into continuations. I pause the presentation for a moment until the auto alarm stops. Oh well, just stopped. So this is just a roundabout way of expressing a history of play in terms of play paths. So that's what holds here. So it's not possible to conditionalize on histories because those measures do not measure histories but play paths. Now the first result due to Blackwell and Dubins is if mu represents the true distribution of play and mu I represent I's view on the distribution of play, and if all mu I contain a grain of truth about the true distribution of play, then all players' beliefs, well, at least I players' beliefs, merge with the true distribution of play. That's quite a strong result. And already proven in 1962. Now there are two other concepts. Good prediction versus very good prediction. It's every round, player I's predictive learning rule yields a forecast, which is an element on the distribution over actions of all players. And the actual reply induces a distribution proper. Like so. So there is a forecast here, and then when in that round the actions are executed, you have a proper distribution. Of course, the predictive learning rules conditionalized on histories as well as the play itself, of course. Now, player is said to be a good predictor on a play path omega if the mean square error of prediction goes to zero almost surely. So if the distance between the forecast and the distribution proper, if the average goes to 0. Now certain players said to be a very good predictor on a certain play path if the actual individual terms, not only the average but the actual individual terms, go to 0 almost surely with probability 1, like so. Now of course the one implies the other, and then there is the theorem from Blackwell and Dubins that if the subjective views on play dominate the actual distribution of play, then player I is a very good predictor with probability 1. Now it's not the case that it's the other way around, so it's not the case that if some player is a very good predictor, then his subjective view on play dominates the actual distribution of play. To give an example, this example is cited from Peyton Young. Suppose 2x2 game where column player plays left 2/5 of the time, and suppose the row maintains a beta distribution with prior beta 1-1. So well, let's just Control M doesn't work in screencast, so I have to do it manually. So, what did the slide said? 2/5. 2/5 is 40%. So, what's the scenario? The column players place 40% left. So, 40% heads. So the probability of playing heads is 40%. Like so. So this is the probability of playing heads. The row player doesn't know this, and he maintains a beta distribution of which the prior is beta 1-1, and the beta distribution has two parameters, alpha and beta, and the parameters of the prior beta distribution of the row player are 1 and 1, and you see that you will obtain the uniform distribution on the unit interval. You see the unit interval here. Now this is a uniform probability because the row player doesn't know anything about play of the opponent. We do know that the opponent plays heads with probability 40%. Now the idea is that the row player maintains a beta distribution that reflects the play of the opponent. So let the opponent does one move, heads. Turns out heads. So in the first round the opponent played heads, and the beta distribution of the row players updated by adding 1 to alpha. So we're now looking at the beta distribution with parameters alpha and beta equal to 2 and 1 respectively. Now the opponent plays another action, which happens to be tails. And now the role player updates its beta distribution by adding 1 to beta, because every time tails is thrown, beta is increased. Every time heads is thrown, alpha is increased. Every time beta is increased, the beta distribution goes to the left hand side. Well, I can show that. So every time tails is shown, you see? Now 4 times tails, I pressed 4 times tails. 4 times tails, then beta is increased 4 times. Now we have a beta distribution with parameters alpha 2 and beta 5. Now let I did now have manually tossed the coin by enforcing tails 4 times, but let the column player proceed to play with probability heads 40% and see how the beta distribution evolves. Toss a coin. So here we have the history. Because I enforced 4 times tails, and by coincidence many times tails were thrown, the estimate of the role player is this beta distribution, while the actual strategy of play of the column player is just playing mixed 40% heads. So let's proceed. Eventually the beta distribution should converge with a maximum, of course, around 0.4. Well, I helped a bit. But yeah. Well, net logo calculation capacities, because I emulated the beta function, couldn't handle it anymore. So let's repeat this experiment, but now only tossing according to probability heads 40%. So let's play it now fairly and not try to influence by pressing heads or tails. And you see on the long run the beta distribution is going to converge to, but it still misses out on the true distribution here. So although we can prove that the role player in the long term is a very good predictor on the actual strategy of the column player, which is play 40%, strictly 40%, it is not the case that whichever beta distribution we obtain, it will dominate this one, because the actual distribution of the column player is to put all probability here on this single 40%, while the hypothesis of the role player, which is a beta distribution, still has to reserve positive probability for the surface below the beta distribution. So this line has a probability of 1, so this is all probability on this line, and the role player has to divide his probability on the surface of this beta distribution. So the probability distribution of the role player, the mu I, the mu 1, will not dominate the probability distribution of the column player. So the true distribution of play by the strong law of large numbers, that the empirical distribution is precisely 40%, is 1, while at any time the beta distribution of the role player gives 0 probability on exactly 0.4, as you will see. At any point of a continuous distribution, this is 0. The probability of any point in a probability density function is 0. So, to cut a long story short, very good prediction doesn't imply that all subjective distributions of play dominate the actual distribution of play. Now, to cite another result of Kalai and Lehrer, we have to define the notion of epsilon closeness of two probability measures. We have two probability measures, mu and tau, and they said to be epsilon close if for some subset of the event space we have that the mu and tau are still sufficiently large, and for all subsets of y the mu and tau differ only a factor 1 minus epsilon. So as epsilon, for example, 0.1, then they only differ a factor of 90%. For all subsets, for all events, all subsets E of y. So this is actually a very strong condition because it demands for all events, even the most improbable ones, so even the small sets, that probability may differ only 1 minus epsilon %. So epsilon closeness is stronger than absolute closeness, you know, you understand with the absolute signs alongside. To demand that probabilities may differ only epsilon is much weaker. So that's epsilon closeness. Epsilon closeness is to demand that epsilon may differ only epsilon. So let epsilon be a small number, and you see that well, in absolute terms the probabilities of those sets differ from mu and tau differ only 0.8, but in epsilon closeness there's still a large difference, a factor 9. So that's the difference between absolute closeness and epsilon closeness. Epsilon closeness is much stronger. So being epsilon close means that not only does a player assess the future correctly, it even assesses developments following unlikely histories correctly. So if epsilon closeness is applied to play paths, then this is the case. Even developments following very unlikely histories, it estimates correctly. Now here's the crown result of Kalai and Lehrer about Bayesian play. If you have two distributions of play and some level of error, then mu prime is said to epsilon play like mu if mu prime is epsilon close to mu. And then the theorem, if mu represents the true distribution of play and mu I represents I's view on the distribution of play, then if mu I contains a grain of truth about the true distribution of play, then mu I indeed epsilon plays like mu for any epsilon larger than 0. It's quite a strong result. Well, other than having a grain of truth about the actual distribution of play, no other assumptions are made, but actually, of course, this assumption is quite a heavy assumption and unrealistic. How do you know for sure? How you can conceive prior to the execution of the game, of the repeated game, that some play path will unfold with positive probability, even extremely unlikely. Now the theorem does not say anything at all that the player learns to predict other players' off-path strategies. So what other players would do in case they would deviate from the true path of play. So that's it. Thanks for bearing with me, and hope to see you on the other side.